This is yet even more example problems for lecture 15, and we're talking about I/O and particularly how the wrapper handles the I/O associated with the microcontroller. And so once again, we're going to kind of delve into that, a little bit different approach. So let's do it. And so essentially, oh God, wish that wasn't there. This is CPE 233, Lecture 15, Example 3. What we've been talking about is I/O associated with RISC-V, and in particular RISC-V Otter, because our RISC-V Otter is essentially a microcontroller which needs an interface with the hardware, which is what the wrapper does. Wrapper provides just an interface to the microcontroller to the external development board, which is, for us, it's a Basis 3 board. And so it's a really important stuff. It's really simple. I hope you understand this, because you can kind of do any of these problems. It makes this problem really simple if you understand it. Otherwise, you have to memorize it, and that's not going to work. So the Otter, as it is, has a memory range of this is the physical addresses of 0000 0000 through 0x0000FFFF. That's the physical memory space for our RISC-V. So what we're saying here is we're increasing this memory space from this to this. Okay, so essentially we added, instead of 16 bits of memory space, essentially have 18 bits of memory space. And so what we want to do here is figure out how many bits, input bits and output bits, can the microcontroller handle. So it's very similar to the last problem. I think I'm gonna go forward on this one. Okay, so once again, this is the high-level microcontroller. But we have here, it's easier to look at this one. We can input a whole bunch of different things based on using the address here as the select inputs for the MUX. Also, we can output a bunch of different things. Essentially, what we're going to do is register all those outputs. We are going to use a decoder essentially to choose which of these registers we're going to write to, and this is the actual write signal itself. So remember, these are just registers. It's kind of like, you know, a load enable for the registers. That's what this signal here, but it's a little bit more complicated because there's multiple registers, so we need to kind of choose which one we're writing to. Okay, so the address, the physical address space is now, from the last problem, 0000 0000 through, I'm going to keep that a little bit separate, through 0x, this is from the previous slide, 3FFFF. That's the physical address space. This is the number of bits dedicated to memory. Okay, so this is physical memory. So everything that's not these bits is essentially going to be available for this I/O bus address to act as a select input or part of a decoder. So the issue is the entire address space is 0xFFFFFFF. That's how many unique addresses I have in the entire space. And so what I need to do here is figure out, okay, once again, this is the entire address space. I have to subtract off the number of bits that are dedicated to actual physical memory, and that's going to be 0x0003FFFF. That is going to be one of our values here, and the other one is going to be times 32, either input or output. This is going to be the same equation for both. Check it out here, and this is the input data width, and this is the output data width. Same address space for both input and output. So once again, this is like the total number of possible addresses. What I'm going to do is subtract off the number of addresses dedicated to actual memory, and then I'm almost done there. Essentially, that's the number of unique addresses, Each of those addresses can control up to 32 bits, so it's quite a bit of I/O on these things. And we will call that done.